Alright guys, let's talk tonight about oxidation reduction reactions. These are also called redox reactions, and you probably hear me calling them that a lot. And technically what they are is they're a type of reaction in which two different things are going on. One thing is being oxidized and one thing is being reduced. What that actually means for us is that electrons are being transferred from one place to another. And these kinds of reactions, there are tons of them. They're really useful and important to us. I mean, a really good example, biologically speaking, is that photosynthesis is a redox reaction. There are oxygens being transferred. And then if you think even further into the other stuff that happens after that, biologically speaking, you think about the electron transport chain and all that, you can see that the transfer of electrons is pretty important because there's a lot of energy changes that go on. And one of the easiest ways for us to check and to be able to keep track of where the electrons are going are something called oxidation states or oxidation numbers. And we're not really going to go into that in this video. I'm going to use them, but I'm not going to talk about how we find them. So if you need some help on how to find those, you can go back and look at your Chem 1 vodcast 6.3, and it has all the rules in it, and we'll sort of talk about how you find the individual oxidation states. So I'm going to sort of assume your knowledge of that as we go on in this video. So let's just look at sort of a regular reaction. I wouldn't say that this reaction is necessarily common, but I mean that results in a really common substance for us. And this is a good example of a really simple redox reaction. And what's happening here is we've got solid sodium. Okay, so sodium is a metal. Okay, and we don't often think of sodium as a metal, but it is. You'll see here that it's stored in some oil here, even though it looks nice and silvery like a metal. Stored in oil because remember it's an alkali metal and they're incredibly reactive in water and even in the air sometimes, so we got to sort of keep that stored very safely. And then chlorine gas, which of course is a poisonous gas, and then we combine those two things and they're going to give us something as useful and innocuous as salt. But what this matters for us in terms of redox is we want to see what the oxidation numbers are. Now, sodium over here on the reactant side is a 0, and so is chlorine. And remember, the reason for that is that both of these things are in their pure uncombined state, and neither one of them are ions right now. So this is sodium metal, this is chlorine gas. They both have an oxidation state of 0. We go over to the product side, though, and it's an ionic compound, and so now sodium has a +1 charge, chlorine has a -1 charge, and if you remember your rules of oxidation numbers that I said you might need to review, monatomic ions, so a single atom, okay, forming an ion, which each of these individually are, its oxidation numbers, whatever its charge is. And so what you can see has happened here then is that sodium has gained an oxidation state, and chlorine has lost an oxidation state. Now, that also corresponds to sodium has lost an electron, chlorine has gained an electron, and so that's essentially the heart of what redox then is for us. So let's talk about this in a little bit, you know, as far as what the definitions are, and then we'll dive into balancing some half reactions, which is really the hard part. So the oxidation part is where we took our sodium, okay, just to refresh again, remember sodium was 0 and went to +1. That sodium lost an electron, so we would say that it was oxidized. Now the easy way to tell that also is that if you look at it, its oxidation number went up. It was 0 and now it's +1, and so that makes that pretty clear. Whereas if we look at our chlorine here, our chlorine was also at 0, but now it's at -1, so it went down, so therefore it was reduced. And what makes this a little hard to remember sometimes is that essentially it's the opposite of the oxidation number is actually what happens to the electrons. So even though sodium gained oxidation state, it lost electrons. Okay, and so that's pretty important. And so we kind of need some ways to remember that. The way that I learned this was Leo says gur. So you think about a lion roaring, and its loss of electrons is oxidation. And then gain of electrons is reduction. Another really popular one that you'll hear a lot is oil rig. Okay, so oxidation is loss, reduction is gain, and again we're talking about electrons. So either one of those two things, if they sort of help you out to remember that, then that will help you to know, hey, this is oxidation, this is reduction, that's what's happening in this case. The good news is a lot of times you're not just asked really what's oxidized, you're asked to actually balance it and figure out what's going on in the situation. So one of the best ways to balance some really complicated redox reactions is to do what's called the half reaction method. The half reaction method basically says you're going to take your reaction, okay, and this is our net ionic equation right here. You can tell that because there's nothing in it but the ions. And then what we're gonna do is we're gonna split it up into two reactions. One that is the oxidation reaction, and the other one that is the reduction reaction. Okay, and that's pretty simple to do. So iron went from 2 plus to 3 plus, so obviously it was oxidized. Okay. And then this one's a little bit more complicated, and it's obviously going to have to be this way because we see that, you know, that's what's left. But if we calculated our oxidation numbers real quickly, which we didn't have to do on the iron because obviously they're given, this manganese here is going to end up being plus 7 over here, okay? And then it's obviously plus 2 over here, so that's what gets reduced. Okay, so that's the first step in the half reaction method. So here's the whole set of rules for the half reaction method. I'm not going to read through those. I would say hit pause on the video, copy those rules down, and then we're going to apply them in the example here on the preceding page, or on the next page rather, not the preceding one. Okay, so here's our reaction, and we've got everything broken up into our oxidation and our reduction reactions, and so we're just basically going to follow along with the rules, and I'll jump back every once in a while just to make sure that you're on board. So first rule, split them up. We did that. And then for each half reaction, step 2 says balance everything but hydrogen and oxygen. And then we're going to add water and hydrogen and then charges as or electrons as charges to balance each of the individual half reactions. Well, the iron part doesn't need any oxygen, okay, because it's fine the way it is, so that's balanced. The atoms of manganese are balanced just fine, so we can kind of skip that part, and we're going to jump right into this add water part. A lot of students have trouble sometimes figuring out why you would add water here, but remember, we're talking about aqueous solutions, so I mean there's water all over the place, so that's not really an issue as far as us balancing the reaction. Okay, so we need 4 oxygen, so I don't just need H2O, I actually need 4 H2O, okay? And then we got to go to the other side and we got to balance out the hydrogen, so 4 times 2 is 8 hydrogens, so if I come over to the other side, that means that I'm going to have an H+. Remember, we're talking specifically about an acidic solution here, and that's why we can put in the H pluses as well. Okay, so that part's balanced, so I've got that reaction balanced atom-wise. This reaction is balanced atom-wise. But remember, what really matters in redox reactions is what's happening with electrons and charges. So we really have to balance out the charges as well. So if I look at this whole thing here on the reactant side for the manganese part, I've got a plus 7 charge. Okay? 8 positives here, 1 negative here, that gives me a plus 7, and I've only got a plus 2 over here. So I'm going to balance that out somehow, and the way, of course, that you balance that out is whatever side has the highest charge, you're going to add electrons to. Can't add them to the other side because I'm not adding any positives over here, I'm only adding negatives, so I've got to add them on the reactant side here, so that's plus 5 electrons, right? Whoops, not plus 5. Totally messed that up. No, I'm crazy. I didn't mess that up at all. So 5 electrons. I forgot to add the negative. I think that's what threw me off there. So 5 electrons to the plus 7 makes this whole thing now plus 2 instead, which is good. That's what we want it to be now. It balances out. We're going to do the same thing down here for the oxidation reaction. We're going to add electrons to balance the charges. A little easier down here because I've got a plus 2 here, a plus 3 here, so 3 plus, plus 1 minus equals my plus 2. So now the charges on each individual thing are balanced, but here's the step that throws people off a lot. We have to find some way to account, to make sure that the electrons basically cancel out. And so if I've got 5 over here, and when I add them together, I'm going to need 5 over here. So the way I'm going to do that is I'm going to make this a 5, but what our rules of algebra say is that whatever I do, I have to do it to everything in the equation, so that's going to mean that I'm going to multiply the whole oxidation equation essentially by 5. Okay? So, whoops, drawing straight lines is hard. I tell you what, let's make this easier. Let's use the straight line tool. Boom! Look at that crisp line. Okay, so now we're going to add, I made a good line and then a bad plus sign. So now we're going to add these things up, and the way it works is that you cancel out things that are the same on both sides. Okay? And then you write everything else down. So real quick, I'm just going to go ahead and cancel out what cancels. I know that these guys cancel out. And sometimes you'll have waters and hydrogens that cancel out. I don't in this case because I didn't have any in my oxidation reaction. But you will a lot of times, so just sort of keep that in mind. So now I'm just going to write down essentially what I've wrote. So I'm just going to bring everything down. So I've got 8 hydrogens, okay, plus 1 permanganate, right, plus 5 irons, okay, 2 plus iron 2. That's going to give me 5 iron 3 plus. We could call them ferric and ferrous if you want, but we don't really have to. Plus my manganese ion, again a manganese 2 plus 4 H2O. Now we're essentially done at this point, but you're sort of you've got a couple of checks here that you need to do. They're the last step, which basically just says now that you've written everything down, make sure that it actually balances. So I've got 8 hydrogens here, 4 times 2 is 8 here. I've got 4 oxygens, 5 irons, 1 manganese, 1 manganese. And then what you should be doing is checking to make sure that your charges balance out as well. So I've got 8 positives, a minus, so that's 7 positives, and then 10 more, so that's 17 total positives. And then I've got 5 times 3 is 15, plus 2 is 17. So my atoms and my charges balance up, so everything's great now. Okay? So that was for acidic reactions. What would we do if it was basic? Well, essentially, and here's the really important part that everyone seems to miss a lot of times, you're going to do everything exactly the same at the beginning, and then we're going to do a little bit different at the end. Okay? So again, hit pause, copy those down real quick, and then we'll work an example. All right, so here's our example in this case. We're going to assume that this reaction is in a basic solution. Looks like it's going to be pretty confusing because this is one of those one product things, and so you're like, well, I'm not real sure what happened here. Okay, well, essentially, here's what's going on here. To balance out the whole thing, to be able to balance out here, we can tell that what happened is that the silver got oxidized, right? Okay, because it's going to have to become, it's got a certain charge on it that's going to matter to us. So that's what's going to happen there. Sorry guys, I knew something was funky in this one, and what is funky is that there should have been a subscript of 2 here. That's why the parentheses were there. So let me draw that in real quick, and then we'll continue with that. Because I was like, there's no reason for that charge there. So silver's got a 0 over here, and it's going to end up with its sort of usual +1 ionic charge over here. Because I've got 2 of these, they have to add up to negative overall. And so therefore I'm going to have a +1 there. Now what you may be saying to yourself is, well, that's great, but what the heck is going on in the other reaction then? So here's what makes this one a little hard. It's actually oxygen, okay, by itself, and you're like, there's no way that that's possible. Remember, this is the step where we're going to add in water, so that's what we would normally do in the reaction if we had oxygen on one side, so that's what's going to happen here. That's going to be our other half reaction where there's reduction going on, okay? So oxidation occurred here, reduction is going to happen here. How does that work? Well, let's go ahead and start working it, and I think it'll make a little bit more sense then. So remember, we're going to follow the same rules we did last time. We're going to balance everything but the oxygen and the hydrogen, so I'm going to go ahead and do that. So that 2 there will take care of that. Down here, I don't have anything but oxygen, so we'll come back to that in a second. So that's balanced okay, and in fact, this whole thing is balanced as far as atoms go, and so we'll have to worry about the charges here in a minute. And I'm going to go ahead and get rid of these oxidation numbers real quick just to be safe. Okay? And then what happens down on that bottom one then? Because I know that's driving you nuts. You're like, there's no product. There is a product, and that product, of course, is going to be our good friend water. And I'm going to need 2 of them because I've got 2 oxygens on the left-hand side. Okay? And then this is where we do our little hydrogen trick. So I come back over here, and I'm going to add my 4 hydrogens. Okay, now remember, this is basic solution, so we're going to clear that up in a little bit. Okay, so now we got to worry about charges. So I've got a -2 charge over here, and I've got a -1 charge on this side, so that means I need to add an electron. Okay, and then on this side, I've got 0 charge over here, and I've got a 4+, so that means I need to add 4 electrons over here. Okay, sorry, I should have changed colors for that step. And so then we have to account for the electrons, right? If I've got 4 down here, I'm going to need 4 over here. So I'm going to do that. So I multiply everything by 4. That's going to make this an 8, right? And then a 4 there as well. Okay, so now we're sort of at the normal step where we're like, okay, that's good, we're all right with that. We want to check our charges, make sure that we're okay, and we are. And then we're going to add stuff together and cancel stuff out, right? Okay, so that's where we would normally get to at this point, is we want to go ahead and cancel out our electrons and all that jazz. My straight line is slightly better this time. Okay, so electrons are gone. Good deal. And so now I've got 4Ag plus 8Cn plus 4H plus. Well, I probably should have written in a different color down here. I'm going to skip a space because we got something we're going to add in here in a second. That's the basic part here. Okay, you'll see what I mean here in a second. So 2 waters plus 4 of that complex ion that we'll talk about later in the year. I don't want to make your heads explode right now. Okay, so that's all we had on the right. Now, so here's where the basic part of the reaction comes in. So real quick, let's just jump back. Okay, to both sides of the equation, add the number of hydroxide ions that's equal to the number of hydrogen ions. Okay, so let's come back over here. Sorry, let me click those back in so it doesn't seem as confusing. So I'm going to add hydroxide. So I had 4 hydrogen ions, so that means that I need to add 4. Let me make sure that that's actually legible for once. Okay, so that means that I've got to add 4 hydroxides, 4 OH minus. Now, of course, what happens right here is that those are going to become water. Okay, let me go ahead and add them over here before I forget about them. Okay, so now this becomes 4H2O. Okay, because hydrogen plus hydroxide is going to equal water. And now that's going to allow us to cancel some waters out. Okay, so let's do that. Those 2 waters are completely going to go away, which, by the way, should make some of you all that were freaking out a little bit about this part, okay, here, feel a little bit better, because those are going to go away. And then we're going to just cancel those out. That's going to leave us with 2 waters on this side. Okay, so now what you would generally want to do at this point then is rewrite the whole thing so that I would have 4 silver plus, I forgot the charge on this. That was kind of a big deal. 4 silver plus 8 cyanides plus 2 water plus oxygen yields 4 of our complex ion plus 4 hydroxide ions. And now that's a balanced reaction. So really the only thing that really makes any difference here in a basic reaction is that you're going to work it all the same way. And then you're going to add these hydroxides in here to turn into waters. You're going to turn your hydrogens into water because you shouldn't have any hydrogens because it's a basic solution, right? And that obviously is going to be the case. I mean, if it's a basic solution, we're going to have hydroxide there. And so that's what we've got represented here in our reaction. All right, guys, I know that's kind of complicated. You might want to rewind, walk back through that a couple times. As usual, if you got some questions, let me know. And as always, we'll work a bunch of examples in class together. Thanks.